Hello everyone. In today's class, we'll see how to draw the dotted equivalent circuit. So we are having two coils in this. In these two figures, we are having two coils wound on a core. The first coil is having a self-inductance L1 and the second coil is having a self-inductance L2. And since both the coils are wound over the same core, they are mutually coupled and they will be having a mutual inductance also. And now we have to find the polarity of mutually induced EMF. We have seen in the last class that if the fluxes produced by both the coils aids each other, then the polarity of mutually induced EMF will be same as that of the self-induced EMF. If the fluxes produced by both the coils oppose each other, then the polarity of self-induced EMF, polarity of mutually induced EMF will be opposite to that of the polarity of self-induced EMF. So we can draw the circuit, equivalent circuit of this. So there are two coils which are connected in series. So we can represent them like this. And now we have to check the direction of flux in this case. So we can check the direction of flux by applying the right hand thumb rule. And this is the right hand thumb rule. That is, if you are holding a current carrying conductor in a right hand such that the thumb is pointing in the direction of current, then the manner in which our fingers wrap around the conductor, that gives the direction of magnetic flux. So applying that right hand thumb rule over here, we will get the direction of flux in the first coil in this direction and the direction of flux in the second coil like this. That is, in both the coils current is flowing in the same direction. So we apply right hand thumb rule, we'll get the direction of flux like this. So that means phi1 and phi2 are aiding each other. And in the second circuit, that is in figure B, we can see that the current is flowing through this direction in coil 1 and in the opposite direction in coil 2. So if we apply right hand thumb rule, we'll get the direction of flux phi1 like this and the direction of flux phi2 as opposite. That means phi1 and phi2 are opposing. So by dot rule, we have seen the dot convention in the last class, and by dot rule it says that if both the fluxes are aiding each other, then the current enters or leaves by the dotted terminal of both the coils. So the current can either enter by the dotted terminal of both coils or leave by the dotted terminal of both the coils. Then phi1 and phi2 are aiding each other. So here the current flowing is I. L1 is the self-inductance of first coil. L2 is the self-inductance of second coil. And we must show the dots now. So since the fluxes are aiding each other, the current must enter the dotted terminals of both the coils or leave the dotted terminals of both the coils. So we can represent it like this. So I am showing it as entering the dotted terminal of both the coils. And now if the fluxes are opposing each other, then the current must enter the dotted terminal of one coil and leave the dotted terminal of the second coil. So I am putting the dot over here. That is, the current is entering the dotted terminal of the first coil and the current is leaving the dotted terminal of the second coil. And here, when the fluxes are aiding each other, then the inductance of each the coil becomes, first coil becomes L1 plus M. We must add M to this self-inductance and we must add M to the second coil also if the fluxes are aiding each other. Then the inductance of each coil gets increased by M. So the inductance of first coil becomes L1 plus M and the inductance of second coil becomes L2 plus M. And if the fluxes are opposing each other, then the inductance of each coil becomes L1 minus M and L2 minus M. So we can write the equivalent inductance of the first coil, that is L1 plus M plus L2 plus M. That means the equivalent inductance becomes L1 plus L2 plus 2M. So this we have derived in the last class, that is when there are two coupled coils in series connection and the fluxes are aiding each other, then the equivalent inductance is equal to L1 plus L2 plus 2M. That we have obtained now. And now the equivalent inductance in this case is equal to L1 plus L2 minus 2M. And this also we have derived in the last class, that is when there are two coils in series, when there are two coupled coils in series and the fluxes are opposing each other, then the equivalent inductance is equal to L1 plus L2 minus 2M. Okay, so if the fluxes are aiding, we must add M to each coil, and when the fluxes are opposing, we must subtract M2 from each coil, from the self-inductance of each coil.